Okay, hello. I am Rene Rideau from Alacris, and this is my talk on building distributed applications in OCaml, or making types your friends, not your enemies. Ta-ta. So, to introduce this talk, I will present first a collection of general purpose techniques that I've been using in OCaml, but I could have been using any other functional programming language such as Haskell or Scala. And these techniques are oriented towards building distributed applications, but really you could use them in general, not just for blockchain applications, but for anything that involves persistence and multiple computers. And I'm a Lisper, so I will tell you about what I learned from going from Lisp to OCaml. And this will be my experience report adopting types, adopting language-enforced types, because they're also types, of course, in Lisp, in any language. And I will tell you the good, where the type system really helped me, the bad, where the type system got in the way, and the ugly, where it really has to improve. My take-home points will be that type functional programming enables programming at scale in a robust fashion. If you want to write large programs with more than one person, and that this program will survive attacks by people who really want to break your program, type functional programming is a way to go. And if you are building distributed applications in particular, monotonic functional programming is especially the way to go. But you pay a steep price by adopting types and system-enforced types. And there are obvious ways in which to improve type functional programming. So let's start with a very simple example of types at work, marshalling. Marshalling is taking data and transforming it to bytes so that you can send it over the network or to a database or to a friend or to something else. And then, of course, when you marshal the data, you would need to unmarshal it back to take those bytes and recreate data from those bytes. And there are many other names to marshalling and unmarshalling: serializing and deserializing, encoding and decoding, formatting and whatever, and parsing. And so you need that anytime you communicate, anytime you save data. So you need that all the time. And there was an old study by IBM. It's old, but I think it's still valid. That in a normal program written a normal program written by IBM, about 30% of your code is just marshalling and unmarshalling. And that's without any advanced error handling. 30% of your code, that's a lot. That's a great sink of labor, and it's also a great fount of bugs and security vulnerabilities, because lots of the code you have that has bugs on the internet is, oh, we forgot some number or out of bounds something while decoding data from the internet. So at the level 1, to process a request, you take bytes as input and you output bytes. At this level, you may as well use C, because the OCaml types don't help whatsoever. OCaml bounce checking does help, but type checking does not help. Of course, instead of C, you should not use a dysfunctional language. You should use a functional language, such as force. So if you use a low level, go force. And the problem when you do these things, the problem of having a shotgun parser, where you're going to decode and do some bit of processing and decode doing some bit of processing, and that's where you mix up what you are doing and where you are. Meredith Patterson gave a talk about that 2 years ago at LambdaConf. She calls that a shotgun parser, and indeed your code goes very fast, just like grape shot fired directly at your foot. So don't do it. There's a whole field called LangSec, language security, that tells you how not to do these things. Okay, but we can use a bit more types. You can, instead of processing byte, you can process XML or JSON or something structure. And in this case, you have dynamic type safety, but you don't really take advantage of OCaml. The type is the same as you would have in Lisp. So why use these types if you're programming in OCaml? You should just write in Lisp. It would be much faster, the syntax would be much easier, the code would be faster, everything would be better in Lisp. Don't do that in OCaml, you're missing the point. So the thing you want to do in OCaml, you have your process request function, take a request, a type that is well defined and has an algebraic data type, and that returns a response that is also well defined. And then your marshaller will be something that takes to marshal, or so in OCaml it's a bit ugly. When you marshal, you side effect a buffer, so you take a buffer, an alpha, and you just side effect it, you return a unit. When you unmarshal something, you take an index into a byte buffer and return an alpha and a new index. That's a bit ugly. That's how we do it because that's what's natural in OCaml. Ugh. But anyway, it works. It's lots of bug-prone drudgery writing all these unparser and parsers, but you can do it. It's still type safe. The problem is that because of this drudgery, you are likely to miss a point where the two should be the inverse of one of the other. So as I did it, my first attempt, I introduced lots of bugs where the parsers and unparsers are not the right thing. So the next step is using marshalling combinators. You say, hey, if I have a marshalling combinator for, I know how to marshal and unmarshal an int, and I know how to marshal and unmarshal a string, now I can take a structure that has an int and a string. I have a function how to decompose this structure into a pair, or to reconstruct this structure from a pair. And now if I know how to marshal alpha and how to marshal beta, I know how to marshal my structure. And I can have like combinators for 1, 2, 3, 4, 5, 6, 7, 8, 9 values in my fields in my structure, and that works. And that's much less bug prone because now with these proper constructors, my marshallers and unmarshalers will be inverse of each other by construction. So it's much better, but it's still a lot of bug prone drudgery. And we can do better. What do? We derive the marshalling from the type. So in Objective Caml, you have something called PPX. It's metaprogramming. It's a preprocessor. It totally sucks compared to these macros, but it does a job. You can take the type, decompose the type. Oh, this type is a structure with 9 fields, so I will make the marshalling and unmarshalling for 9 fields, etc., etc. It works. And you can save tens of lines of code for every structure you define. And after you define a few hundreds of lines of structure, you have thousands of lines of code you don't have to write. That's great. Of course, level 6 would be to use GADTs, generalized algebraic data types. And then your process request would be alpha request to alpha response, where alpha has to match, and that's much better. Problem, a lot of the PPX extensions we use do not support GADTs, so for us it's still a to-be-done item, because we'd rather have the automation of the PPX than to have the safety of the GADTs. The safety you gain from the GADTs does not compensate the lack of safety you lose by doing all this stuff by hand. Okay, so we've seen with marshalling how types can help you do things much better already. So it's a case study in how types help. If you follow the type instead of going against the types, you get a lot of code saved for you and a lot of safety gained. Okay, so now let's generalize to monotonic programming, things that we can do besides low-level marshalling for distributed code. So what I want to introduce is the notion of monotonicity. You know purity, you know pure functional programming where there is no state change. Well, with monotonicity, you can have state change, but only one way. So you have some notion of this state has more knowledge than this other state, and you can add knowledge. And you can never destroy knowledge, you can never invalidate previous knowledge. And this style of programming is used everywhere. If you have ever computed a least fixed point in any algorithm, you're actually using monotonic programming. The intermediate state of the knowledge you know about the things is monotonic until it converges, and then it's the final state and it becomes pure. Git, if you've ever used Git or any system like that, it's about monotonically adding information to your tree of data. CRDTs, I don't remember what the word stands for, but basically it's distributed programming where the actors in the system send each other information, and the state of what they believe about the common state only increases and never decreases. So it saves you a lot of synchronization. You never have to guess where the other guy is. You just send the incremental information, and it converges magically. Append-only logs, append-only databases, same principle, monotonicity, uses it everywhere. Actually, if you use a lazy functional language that does not always terminate, you're already using something that's not quite pure but monotonic. Underneath, if you look at how it's implemented, you have some kind of flag that says, is the result there or not? And if it's not there, compute this chunk, and if it's there, prepare the result. But of course, no computation that terminates will ever see that there was something amiss, because that's how it happens with lazy evaluation. By the time you see the result, you've seen it, and if you don't see it, you're dead, you'll never see it. So it's not quite pure, but you never see the difference. And that's exactly the definition of monotonic. It's not quite pure, but you never see the difference. So what do we do in a monotonic way? We use a content address storage. Content address storage is the same as your usual graph. You manipulate a graph of data. But instead of having pointers to memory, you have, that is, your pointer is a digest of the content, a cryptographic digest, a hash function. So, you know, SHA-1, SHA-256, whatever. And this is your address into the thing you're pointing to. And the advantage is that everyone in the network can agree that the pointer to some data is its content. It's very robust. You have to make usual cryptographic assumptions about that. You also have to make sure that your basic graph is a DAG, direct acyclic graph. You are not allowed to have cycles. You can represent data with cycles in the usual ways, or trivial ways to represent data with cycles as data with no cycles. Use whichever you like, but your basic graph needs to have no cycle. And in a context like that, with styled programming, we can have a simple function to extract value from the database based on this digest and unmarshalling function. You take the digest to make a key out of it by prepending some prefix. You get it from the database, and you extract, you unwrap the option because you know it's there. Yeah, of course, if I have the digest, of course it's a database, so I can just unwrap the option. And then you unmarshal it, and there you go, and it's all typed. It's no mistake possible. Great. Okay, then you can abstract over content addressing, because I want to write a trie data structure. Trie is a Patricia tree. Whether you know what it is or not, doesn't matter. It's a variant of binary tree that's very practical for in the monotonic setting. And I want to write my trie data structure in a way that abstract over whether it's pointer in memory or wrapping over the database. So I will have a wrapper here in my module interface, type alpha wrap. And I will say, hey, tell me how you are going to wrap it, and I'll wrap it for you. And when I define the type for a trie, I have the wrapped type, which is T, and I will have the unwrapped type, which is in this case trie, which will be either a leaf or a branch, or the actual type has a bit more elaboration for a trie. But what's interesting is that when you recurse, you wrap the thing before you recurse. And of course, when you use the identity wrapping, it's just the usual trie in memory. But if you want to have it persist in your database, you just change the wrapper by a wrapper that does the persistence in the database. Perfect. And then you can write higher order modules that don't have to care how the thing is or isn't wrapped, and that will work as well with this database or that database or in memory. Okay, so is that an effect though? If I unwrap, if I come to read from the database, isn't that an effect? Read it from the database? And the answer is that yes or no. If you're looking at the database, it is an effect. If you want to just write your application in a pure functional style, you want to not consider it as an effect and consider it, I'm just working that graph, and the graph is pure. So semantically, it's pure. So depending on the level of abstraction at which you want to look at it, it is pure or impure. And same with logging. When I log something, I just want to get a trace of what's happening, but most of the time I don't consider that as an effect. It's not something I want to pass as a monad or something to make all my program complicated. Either it happens or not. It needs to follow my program. My program does not need to follow the logging. And of course, lazy evaluation, I told you, can be an effect or not, whether how you look at it. Allocation of memory can be an effect or not, depending on how you look at it. Everything can be an effect or not, depending on how you look at it. When you implement something, the thing you implement is an effect. When you use it, you want it to not be an effect. You want to be done by someone else. So everything is an effect when you're doing it, and everything is not an effect when you're using it. So lenses. Okay, everyone knows lenses here? I suppose everyone knows lenses. It's just a pure functional way to access and modify data structures. So a lens will be, you have a data structure alpha, and in it you have a subfield of type beta, and you have a function get that will take the beta from the alpha, and a function set that will give you a new alpha from a new beta. And that's how you can do all your modification in pure style. And all you need to do when in a monotonic setting is that you have your head variable that you will update monotonically after having modified the contents in the pure way. Fine. Zippers. Zippers is kind of zippers as I use them, or is kind of an alpha length, but instead of being function, it's data. There are many variants of zippers. That's the one I use. And what makes it interesting is, well, we'll see right next. So here's how I zip in a binary tree. A zipper takes a binary tree at the bottom, and you want to reconstitute the binary tree at the top by saying, oh, to get from the top to the bottom, or to get from the bottom to the top, I need to add another tree to the right, here another sibling tree to the left, another sibling tree to the right, to the left, to the left, to the right, and I get back to the bottom. So to unzip the zipper, you take your T at the bottom, and the path where you add to left and right other trees, and you reconstitute the tree at the top. And that's why it's called zipper, because and you have a function find path, which will find a key in your tree, and will find the closest subtree to that key. And if the key is found, the closest tree will be a leaf. If it's not found, it will be not a leaf. And finally, bad indentation, I have a function called path map. If you have seen, my path is annotated by type alpha there. And my function path map will change the alpha to something else. So when I have a tree, my path will be made of T and will be made of actual trees. But when I want to get a Merkle proof here, all I have to do is replace the trees that are my siblings by their digest. So to get a Merkle proof that a tree contains a certain key, all I need to do is give you the key, give you the digest of the tree, give you the leaf, the digest of the leaf, and give you the path where I have replaced every tree by its digest. So now I have a structure of logarithmic size that is a verifiable proof that at this key in that tree there was this thing. And this is done in like a few lines, like longest function is 7 lines of code because we have this abstraction of data structure. So if you have type abstractions like that, you can do something that for other people is lots of ad hoc code in a very nice, very elegant way that is like obviously correct by construction. Very nice. So types are useful, and I think that's all I will say about monotonic programming. I have a library with lots more code, but I don't think it deserves discussion here. I would want more to discuss now the benefits and costs of using types. So why use OCaml rather than Lisp? Once again, I was writing cryptocurrency applications where we cannot afford having a single bug. If you have a bug somewhere in your code that faces the internet, you will lose all your money, or you will lose all your customers' money, and then someone very angry will come at you. Either way, you will not be happy. So bugs make you unhappy, and you cannot afford a single bug. It's much worse than even if you write hardware, because in hardware, the bug, you can say, oh, just don't do it. But with a bug in your cryptocurrency code, you can't tell the attackers not to do it. They will do it on purpose. So the static bug types find bugs before deployment. Actually, if it finds bugs before deployment, by definition, it's static type. It might not look as a type to some people, but it's still a type to people who are abstract enough, like we are. So types also critically communicate design constraint to coworkers. When I started this project, I found I will not be able to finish this project alone, so I need to have types. And whether they're enforced or not by the system, I need to have them. When they're enforced by the system, it's easier to detect if one of the workers has failed. Parametricity enables me to have robust abstraction at many levels. I will discuss that later. And putting type first forces you to ask the important questions. By having this system that is strongly typed where you have to put types to everything, you have to ask the question, what is the actual structure of this? And the downside, of course, is that, or many downsides to use OCaml versus Lisp. First, the type system rejects the Lisp easy solution. As a Lisper, oh, I know how I do it. Tap, 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 tap. Oh, sucky OCaml syntax, but I can survive. Tap, 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 tap. It doesn't type. Oh, it cannot type. Oh, the OCaml system cannot type possibly that. So the type system starts as being my enemy. I'm trying to write the solution I would write in Lisp, and not only the type system won't do it for me, it is such that it's not even conceivable to write my program. So that's very frustrating, and I start using OCaml being very, very frustrated because it prevents me from doing what I need to do. the syntax is a hindrance at many levels, meaning that the OCaml syntax is not nice. The way there's no good way to all the way to indent the OCaml syntax are bad. There's no good way to indent it. Especially when you start using monads or anything, get things that are either too nested or that break your indentation strategy. Nothing is good. And of course, there are no macros, it's impossible to extend, and there's this ppx mechanism, but it's itself ugly. And there's no way, syntax sucks. Type first is cool sometimes, but it also makes exploration harder. In the beginning of the project, I had no idea what was the structure of Ethereum, and I still need to put the types. So you need to put the types before you know what the types would be. That sucks. That's like lots of wasted time and stupid effort that leads to nothing. So there's a cost to putting the type first. The types errors can boggle the mind. Sometimes you have a type error. What the hell is going on? And it took me weeks and weeks to learn how to not do the thing that could possibly trigger those type errors, because that's horrible. That said, with Lisp, when you have macro errors, that can also boggle the mind, so that balances out. Dynamic evaluation is slow and awkward. If I have anything that depends on user input or configuration input, evaluating it will be very awkward syntactically and very slow at runtime. So most of programs don't have a lot of that. That's okay. But sometimes you do have a lot of that, and then, Any design patterns are repetitive and error prone. So we see there are ppx that exist that can automate some of these design patterns, but since ppx is very high bar to doing it and not composable, it's very badly done, you end up doing a lot of repetitive design patterns and churning them by hand, and that's not nice. That's a clear downside of OCaml and functional programming over using Lisp. So, but there are some bugs that are wholly eliminated by types. And of course, there's an obvious bug. Oh, I put an int instead of a string return for an int. It's caught immediately by the type checker. Yay! But also the fact that all the functions will be properly called in my API, which means that I don't have to worry that my coworkers will use the wrong types when they call me. Much less checking to do. The patterns are exhaustive. That's great. Which means that if I have a sum type, the OCaml will tell me, hey, you missed this case. And that's something you don't get in Lisp or at all. Or in Lisp, maybe you write tests for the end user, for the end question, but in all the intermediate functions, the OCaml type checker does that for you. That's great. Similarly, if there's an error you didn't fail to test, and the type says this is a monad with an error monad, and you fail to test the error, it will shout at you and, oh, I know I need to handle this error. What is the greatest part is incomplete refactorings. If I start refactoring my code, and you do that in Lisp, well, you will forget to refactor part of it, and oh, the test failed, or the test failed to fail, and it's even worse, and you'll have a hard time later on finding where you failed to complete your refactoring. But if you do a refactoring with Objective-Caml, the type system will keep shouting at you until you're done with its refactoring. And by the time you are done, it will just compile, run all the tests, and everything goes well. And of course, this abstraction violation, this is a parametric polymorphism. If you write your code in modules that import just the types of the minimal interfaces, you know that all the bugs you write will be bugs within this abstract thing. So you can't do bugs that go underneath this abstraction barrier. And that's actually the greatest part of types, I believe. So bugs not eliminated by types, of course, the bugs, logic bugs within your module, the configuration bugs. Sometimes I do my code refactoring, at the end I forgot to update the configuration, whoops. Integer interval errors, the OCaml type system does not deal with that. Concurrency issues, some people use things like session types, but they only work so well, and then you have to rewrite all the interfaces to everything to make them happen. It's very heavy to use, and it only solves so many issues. Concurrency issues are still a big problem in OCaml, at least the way I use it. Insufficient error handling, just because you need to handle an error doesn't mean that you're actually doing it correctly, and this crops up everywhere, and that's scary. But what is good about all these bugs that are not eliminated by type is that by restricting the interaction, these bugs are much fewer and simpler than the bugs I have when I don't have this type infrastructure, which means that they fit in a brain, which is important, which means that now I can fix them. This is not always strictly true, but the more I use the types in the right way, the more it is true that the bug will be smaller and simpler and fit in my brain. So that's good. performance-wise, it's a wash. With static type checking, I can skip all the runtime type checks. Yay! That's a 2% of performance gained. And the types enable many optimizations, although in the OCaml case, since it's the optimizer is a bit, it's not that optimizing, and also it cannot take, it cannot assume purity because OCaml is not a language that's pure by default, so there are lots of optimizations you could do in Haskell that will not be done in OCaml. Nevertheless, you can do a lot of optimization that you could not do in Lisp, for instance. However, anything that's dynamically evaluated will be actually slower and more awkward. And the fact that you can't have macros or that it's so hard to write macros or to extend the compiler means that a lot of the macros that in Lisp you would write to increase, to inline the thing that you know to inline or to optimize some patterns, you can write a macro or compiler macro in Lisp that's trivial. In OCaml, you won't do that because it's too expensive, and so you lose a lot of performance there. So it's a wash. Monads versus Lisp. In OCaml or in Haskell, you have all these monads, error monad, state monad, etc. You have all the same things in Lisp. You have error monad, I can raise conditions. State, I have assignment, I have present future, the reader monad. Oh, you've reinvented dynamic variables, congratulations. Control monad, oh, you've reinvented partial continuations, congratulations, etc., etc. So everything you can do with monads, you can do it just as well in Lisp. But there's still something you gain. You gain that you make the effects explicit. So you can reason about the code. Oh, this code does not use the reader monad or whatever monad, so I know it will not have this effect. So you make what effects you use explicit, and that forces you to think about which part of the code is responsible for what. And that can be good. That also has a cost, because now you have to do it, even when it's obvious. With the Lisp programmer say, oh, of course it's obvious which part of the code does what. Now, the OCaml programmer, you have to painfully make it happen. Sometimes you can introduce new features that your implementation does not support, but isn't it stupid that your implementation does not support it natively? Maybe yes, maybe not. I think the important part with Monad is that it allows you to build higher tower of structures. There were plenty of talks at LambdaConf this year where people build higher structures, monads, free monads, or free applicative, or something like that. And that's where it shines. If you use just a simple monad, it's not a big advantage with respect to using Lisp. But if you use towers of structures, that's where you can build really powerful things that is correct by default, correct by construction, and where you know that there is no bug due to lack of parametricity. I will rant about a monad that the syntax is way too low level. When you use monad directly, it's like equivalent to continuation passing style. When you use the famous do notation, also much better. No, it's just a normal form. It's still like far from the power that you have in Lisp to just use a nested expression. And actually, I think you could solve that in Haskell if you were not so entranced with a normal form that you thought it's the panacea. If you say, oh, I can write this macro that does nested expressions instead of a normal form, you could be so much better. So future improvements to type systems. If I wanted a type system where I could do the things I like to do in Lisp, first I would have to do the objects right. So OCaml objects are tool method in many ways, while OCaml modules do not support late binding or fixed pointing right. So there is no great solution in OCaml to use objects. A style of object programming I love is prototype inheritance. Consider Nix, which is pure, functional, dynamically typed, and lazy. Perfect. I mean, the only thing it doesn't have is types, and you can have then in 6 short library functions, very short, you can have prototype inheritance. It's a beautiful way to write objects. Without types, the cake patterns actually works and works great. You've heard of a cake pattern. Oh, don't use a cake pattern in Scala, it doesn't work. Well, in Nix, it works beautifully. And you can have that in 6 short library functions, and you can't type that, of course, in Haskell or OCaml or Scala or anything, because you will need to type that appendable row types, and I think only Urweb and Ermine have that. Multi-methods, method combinations, meta-object protocols. You've never heard of that because most object-oriented programming language are 50 years behind Lisp in terms of object-oriented programming. But coming from class, I miss that. Okay, schema upgrade. Any real program deals with data which will persist. If your program does not deal with data that persists, it's a game, it's a toy. It's not a real program. So to have a real program that uses persistent data, well, these days you can't use any modern programming language because all modern programming languages are toys, like whether it's Haskell or OCaml. The only one that's not completely a toy is Erlang, actually. Every programming language is a toy. So use a database. And the database, they have an integrated programming language, which is horrible, totally misdesigned programming language. So you have language for toys and non-toys with bad programming language. That sucks. You would need to have both. You want to have both together, where you can write your language in which writes your process and object and just works. And in Lisp, it's hard, but you can do that. And it all even supports Schema Upgrade, because your data will change over time, because otherwise it will bit rot. Can any static type system do that? Does any static type system even attempt to deal with Schema Upgrade where the type of variable changes from one version to the other? I've seen no such thing anywhere. So if you want to do with type system the things that I can do in Lisp, but I casually do in Lisp, you need to add that to your type system. Of course, better effect typing and syntax. Well, monads are semantically awkward. It's very hard to add an effect or remove an effect. It's painful. Monad notation, I already discussed how horrible it was. Jane Street apparently is funding effect typing for OCaml. I don't know what will happen to it, when it will come, and how nice it will be, but that will be definitely a good thing. But the thing that bugs me most about effects and typing is that, once again, one man's pure bliss is another man's effect. Sometimes I want to deal with this database as it's pure stuff. Blockchain is pure graph of data. Sometimes I really want to dig into it and poke inside the implementation and say, hey, I'm reading from the database, and here we would really like to do it with explicit monads or explicit effects. So for that, I will really need compile time reflection. I want to have something to implement refinement logic, where I can say, this is one level of abstraction, this is another level of abstraction. There is a correspondence between the two. The abstraction is never violated, even though at one point it's pure, and at another point it's effects. I want to have that. And I want to have that correctly, which means that eventually I probably need dependent types. But even without dependent types, I want at least to make an explicit difference between these multiple levels of computation, so that they don't mix and match and you don't introduce failures, inadvertent failures by violation of abstraction. And when I do compile time reflection, what I will want to do is extend my types with domain-specific fragments. Sometimes I really care about resources. I want linear types or affine types or unrestricted types or with what, I don't remember. I want modal logic with temporal or epistemic logic. I want sometimes have a finitary fragment so that I can clearly compile some things to hardware or compile it to cryptographic circuits or something like that. And of course, I want to everything like that with a system much better than PPX or whatever template Haskell system you have, which totally suck. I want a system that is composable. I want macros. And why can't I have both types and macros? After all, a macro, anything it does based on static information deduced from the source code. So anything that the macro uses as input is a type. By definition, a macro uses types. Conversely, anything you do with a type level programming, anything your compiler does with types, is a compile time transformation of source code. So types and macros are the same thing. Why can't they live together in peace? I want both. And happily, there are people who work on that. There is a famous paper from Popple 2 years ago, type system as macros, and there is Hackett, the language Haskell and Racket. So some people are working on that, but it's very disappointing that there are not more people working on it, because this is clearly the right way to do things. And I want not just compile time reflection, I want also runtime reflection, because I want, for instance, to provide the safety and performance of my compiler to the dynamic code. Why should I have to reinvent a bad compiler with bad optimizations and bad error messages and a bad type system when I could just reuse the same compiler infrastructure for the things that I know at compile time and the things that we'll know later at runtime? I want to virtualize my programs. I want to be able to have a program that has some kind of a free monad or other effect that says, hey, I'm outputting that to the console, I'm outputting that to a sound card, and not have to deal in any way whatsoever with the console and the sound card, actually not having the security capabilities to access either, because this program is not supposed to know anything about the hardware. But instead, a back program will handle, hey, he's writing to the console, so let's open a window, do whatever. And he's writing to the sound card, so hey, for now the sound card is on this laptop, or it's for this whole conference room, whatever. And the fore program should not have to know anything about the actual hardware it's connected to. The back program should have to do it. So that's virtualization not done right at the program level. So you define just the free monad or whatever for the effects that you care about, which means you need fewer security capabilities, which means now you can write an operating system where you have strong capabilities and where the security is manageable at all. I want also to have instrumentation, so I have a whole talk that I gave a previous year on first-class implementation, where I can do instrumentation, I can do code migration, native garbage collection, and I can do, for instance, in this case, I could do integration between the garbage collection and the cache to this monotonic database. I want to have good integration between the two. I can't really have that in OCaml. So there are lots of things I want to do that require runtime reflection, and I don't have that in any existing type language. I want that. So in conclusion, I think that type functional programming enables robust programming at scale. You can write much bigger programs than you could if you were alone. I think a genius like Aaron Su, you see he writes tiny compilers in 7 lines of APL. That's great. Most of us can't do that. Most of us need to work with other people, and for that we need types or some way to build things that are robust despite the fact that other people are idiots and you are idiots. We're all idiots. The types keep us safe. Monotonic functional programming is especially fit for distributed applications. I discussed that, but you pay a steep price for those types. If you think, oh, it's magic, I pay no price for using types, you're fooling yourself. You do pay a price, especially if you're coming from Lisp. You see that you lose all this syntactic abstraction you don't have in Haskell or OCaml. You pay a steep price, but you get something for it. I think in this case of blockchain application, it's totally worth the trade-off. For other applications, I would say it's not worth at all. There are many obvious ways in which we could improve type safety, and I discussed them. And if we step back, my meta story is that types can be your friends or your enemy. If you come to type programming with types as your enemies, or decide that I want to do the thing the same way I was doing before, and then the types get in my way and prevent me from doing it, you'll be very unhappy. And life will be happier if the types use them as your friends. And you say, hey, okay, if I follow the path that the types lead me to and use them as my guide, I can write code that is different, but that will actually be robust, and the types will help me along the way. And they will do the heavy lifting. They will remove the bug from me. They will do lots of things. And that's where I like to tell a fable. It's a fable told by La Fontaine in France, L'ours et l'amateur des jardins, which is itself based on a fable from some Indian storyteller. It tells about this farmer who befriends a bear. And the bear does all the heavy lifting. He's strong. He does the hunting. He swats away the bugs, while the farmers build the farms and yield the crops and does honey for the bear. So they all live happy together. But the bear is a bit dumb. And some days the farmer is sleeping, and there's one of these bugs that refuses to go away, and the bear swats and can't make it go away. So the bear takes a big rock and smashes the bug, and of course the head of his poor farmer together. And the moral of the story is sometimes it's better to not have a friend than to have a dumb friend. And I will say the same thing about types. If you let the types do the heavy lifting, and you know when to use them and when not to use them, when to be with them, when not to be with them, how not to be asleep when they are in charge, you can have a great time. But dumb types are not always your friend. Sometimes it's better to not have dumb type as your friend and go back to Lisp, or to improve the types and make them better. So OCaml type friends are decent. They could be better. Sometimes they're exactly the thing you want to adopt, sometimes not. And thank you. We are à la Chris. We are either hiring or going bankrupt and looking for a job. I don't have a constructive proof yet. So I'm assuming that I'll be hiring, but not sure. On the other hand, if you have extra millions, we are raising capital. If you are interested in working on this kind of thing, we're also seeking research grants with proper partners, academic partners or non-academic partners. And if you want to see the code that I was discussing, this is a repository with the code. And thank you. I think now I have time for questions.
Async or LWT?
I made the mistake of using LWT at some point. I think neither, I don't like either, I don't love either. I think overall the Jane Street ecosystem is more consistent and has better support and better maintained. I object to some of the choices, but I prefer a library where I object to the choices that is maintained to a library where I object more or less the same changes and it's not as well maintained. So I made a mistake. I chose LWT, but if I had to do it again, I would choose async. Other question?
A little bit more of a meta question. So I'm going to disagree with you, but I'd like to understand why you think the way you do. So from like specifically about types.
Yes.
So like practically I work in mostly functional Scala, and a lot of times I have to play with a lot of Python code, other languages and so forth. And I've come to the conclusion that even if I had to write like Fibonacci, like man, I would prefer types always. I've never seen a situation, honestly, I've never seen a situation where I'm like, put up.
Well, maybe you haven't seen a situation where you don't need types. Okay, this gentleman says that he's using Scala with types and types are great and for everything. Well, if you've been raised with types and you've never used Lisp and you've never done all the things I've done in the past in Lisp, like the thing I've discussed before, you've never done that. You don't see the value of it. Like you're a fish in the sea, you don't see water and but if you come from Lisp and you've done all those things, and in Lisp they were maybe not trivial, but they were doable, and then when they were done, they were great. And then you come to type functional programming, and it's horribly hard to do it, and even the result is horrible. You may have been to Tony Morris' talk like yesterday about he does things with extensible type. It's absolutely horrible, horrendous in Haskell. It's possible, but totally horrible. In Lisp, it's trivial. And I've done so much more in Lisp. And okay, you don't have the same static protections, but in terms of expressing the semantics you want, you get it. So do you want to not have the semantics you want? You're protected, but you're also protected from the thing you want. Or do you want to have the thing you want, but not protected in other things that you know how to make do because there are other techniques to make do with them in Lisp. So there are things that you don't see because maybe you've not been trained to see them, and it's a trade-off. It's not a unilateral win. If you think it's a unilateral win, I believe that it probably you need to try more things and expand your horizons.
What about just gradually typing a Lisp instead?
Yes, so a lot of people are working on gradual typing. I think it's the great thing to have. The gradual types that I've seen work so far are not super expressive, so the level of expression is not great. I know that, for instance, in type trackets they are working on it, they're adding dependent types to it. I have no idea what dependent types mean in type tracket, but they're working on it. It's not the same thing that I want from a type system. One type system, I really want the parametricity. I really want the object-oriented support. I think like ad hoc polymorphism and parametric polymorphism are dual to each other, and languages that have only one and not the other are totally brain damaged, like you have like half of your brain. It's stupid. Parametric and ad hoc polymorphism are dual to each other. And that's why ad hoc. That's the thing you have with classes. And Haskell has type classes, so it's not zero in ad hoc polymorphism. You take Haskell before type classes, it's a language good for the trash. But Haskell with type classes is a good language. And it's ad hoc polymorphism, and people say, we can despise object-oriented programming because we have Haskell. No, don't despise it. You already took the major point from it, ad hoc polymorphism. So no, you should be grateful to it. You should not be, it's crap. No. And similarly, C++ has adopted template, for instance, and Java has adopted type parameter. So they have adopted functional programming in object programming have already enriched each other. But if they could recognize that the two things are dual and not one hacked on top of the other, they could go further and have better things, do better things. Yes?
So you talked about macros in Lisp, you talked about PPX in
Yes.
OCaml.
Yes.
How do those compare with, for example, template Haskell, fuzzy quoting, and generics?
I'm not specialist enough in Haskell, the Haskell variants. I've seen them, but what I like to say is that Haskell people like to speak about composability, etc. Template Haskell, PP, etc. are not composable solutions. Macros are composable solutions. So if you are so proud of being composable, learn macros and do it. The theory has been done. Now it's just a practice to be implemented. Like the guys from Hackett, the guys from these Northeastern guys have done it. The theory of mixing types and macros. So it's better. Template Haskell, etc. are better than nothing, and PPX is better than nothing. But it's nothing to be proud of, frankly.
Yes. You also, sorry.
No. Yes.
Similar question, because you said that you would like to have compile time reflection.
Yes.
And I think Haskell generics does some of that.
Yeah, you have plenty of Haskell extensions, etc., etc. There is something. Haskell is not. I don't think it's pre-principle. I think that Haskell is not as good as it could be in this way. But that said, I'm not a Haskell specialist, so. But from what I see, it's very complex and not as composable as it should be. Once again, composability is key. Macros are composable. The Haskell solutions do not look composable to me. Maybe they are. I mean, no? No? Okay. Yes, no, Vlad.
Yes, so like a follow-up to that comment about Python and Scala. So listening to this like kind of like a short encyclopedia of applied philosophy of types versus non-types, I feel like, okay, why not like have the same thought but with Scala versus Python? Because like everybody like loves Python because they don't understand types.
Yes.
So,
and when I'm speaking to an audience of mostly type functional programmers, so I will emphasize the advantage of Lisp. But if I were talking to an audience of Lispers and Pythonists, I will emphasize the importance of types. Well, you're totally missing types. You haven't done this, and like there's a universe of things you could be doing, even in Lisp, even in Python, if only you had types in mind. One of my calls to fame in Lisp is a library called Lisp Interface Library, where I combine parametric polymorphism and ad hoc polymorphism, and it's beautiful, the kind of things you can do that no one else has done. So I invite you all to read my paper on my ILC 2012 paper on interface pricing style.
can you just add that link to your slide?
I'll add that link somewhere, yes. But you look François Rene Rideau, International Lisp Conference 2012, and there's a beautiful paper, and everyone who likes types should like this paper, even though it's all dynamically typed. But it uses, for instance, linear typing to do things you can't do in any other language. Yes?
So if you were going to do this in Lisp, which Lisp and why?
Well, in the long run, I would bet Racket. Why? Because it has a vibrant community about extending the language. It continues the tradition of having languages you can extend. If I needed a Lisp today for production, I would pick Gerbil scheme, which is kind of Racket modules on top of Gambit, because it's ready for production. It's done by people who care about production. If I wanted the long run, I want to have the types and macros at the same time. There is one group of people who do it, the people who work on Racket. That's what I want in the long run right now.
So more scheme, less common Lisp.
I spent a long part of my career writing code in Common Lisp. I left it. I think the Common Lisp community is dysfunctional. The Common Lisp is a language that is frozen in the past, a glorious past. In some ways, the Claude object type system is still 50 years ahead of everyone else in terms of object-oriented programming, but it's not getting better. And
do you have a point of view on closure?
Closure is interesting. Clojure is interesting in many ways. It's also practical-minded, and it has some kind of abstraction ceiling. And I like high abstraction. That's why I like types. So even when I write in Lisp, I like to put types as comments, and I like to build abstraction in Lisp. That's just me, so that's not typical for a Lisper. But Clojure is not very friendly to this style. And for instance, I've written monads in Clojure, and the debugging is horrendous. You don't have the types to help you, and you don't have a good runtime debugger to help you either. So, yes, in Lisp I can write monads, the types don't help me, but the runtime system, the debugger, etc., help me. So I can write my monads and debug it in Lisp. In Clojure, my monad, So no. Clojure is good for, and don't say that Clojure is bad, or Clojure is good for what it's good for. It's not good for what I like to do. Finished?
You're done.
Okay, thank you very much.